All right, so if we know that a conic section is defined as the set of all points that satisfy a certain criteria, then what is that for an ellipse? An ellipse is the set of all points in a plane where the sum of the distances from two fixed points, which we call the foci, remain constant. And in the same way with parabolas, when I say it out loud like that, it sounds a little complicated, but it really isn't. So let's break that down. So suppose we have two fixed points. Each point is a focus, and the two of them together, we call them a foci. So we've got two foci here. And if I were to draw a distance, or find the distance between a point there, and let me just go ahead and make that a little bit larger. And if I find the distance from a point to one of the foci, and find the distance from that point to the other foci, we have D1 and D2 here. We see that D1 plus D2 is going to give us some value, some constant. And any point where the distance between that point and the focus and that point, same point to the other focus, in this case, this is my new D1 and this is my new D2, as long as that sum is the same as this constant that we found earlier, then that is a point that lies on our ellipse. In other words, any point whose distance from one focus to the other focus, where the sum of those two distances remain constant, are points that lie on an ellipse. So with that in mind, let's actually break down some of the key components of what an ellipse has. And this is going to be important for us as we start to understand the standard form equations of an ellipse. So on every ellipse, we already know that we have the two foci. The endpoints of an ellipse can be either the vertices or the co-vertices. We have the center of an ellipse, and somewhere along what we call the major axis, somewhere along this major axis are our foci. So the major axis is this line or this axis that runs through the center, it runs through the vertices, and it also runs through the foci, wherever they might be. We're not exactly sure, and we'll talk about how we can find where our two foci are. But somewhere in here we have some foci. Now, so the major axis we recognize is then the line that runs through the center, the vertices, and the foci. And we are going to label, let me just do this in a different color, the distance from the center to the vertex. We're going to call that value A, okay? Now, perpendicular to the major axis is something that we call the minor axis. This would be the minor axis. And the endpoints of the minor axis are known as our co-vertices, or CV, often I'll write for short, but this is going to be a co-vertex. So we have co-vertices here. And the distance from our center to our co-vertex, one of our co-vertices, is going to be B. And then finally, the distance from our center to one of our foci here, this here, the textbook uses the variable c to describe this, but I actually like to use a lowercase f because it helps me see that it's the distance from the center to one of my foci. Now, there is a relationship here between A, B, and F. Well, what is that relationship? Well, specifically, if I were to take this distance of A that I've just found, so this entire distance of A right here, if I were to take that same distance of A, and let me just draw it again right over here, if I were to take that entire distance of A here, and I were to place it at the co-vertex, one of the two co-vertices, it turns out that exact distance of A is going to meet my major axis or cross or touch my major axis at the focus. So we see here that this, let me kind of draw this again so because it kind of got buried here. This is my F value. This here, again, half the length of my minor axis is my B value. And this hypotenuse of this right triangle that I've just formed, this is the length of my major axis. And clearly here we can see that it forms a right triangle. So we would then be able to say the following. We can say that b squared plus f squared is equal to a squared. And put more simply, we can then say f squared is equal to a squared minus b squared. Okay? So a couple of other summary notes here. We know that the major axis is the axis that runs through the center, your vertices, and your foci. So we can then say that your major axis length then is twice the value of whatever your A is, since A represents the distance from your center to your vertex, or one of your vertices. Your minor axis length, is then going to be 2b, because it's twice the length of the distance from the center to your co-vertices. So now that we have those defined, let's go ahead and let's break down the standard form equation of an ellipse. So let's take a look at this first one over here. Let's just take a look at this equation. You'll notice that it looks really similar to what we have seen previously. It actually looks a lot like that of a circle. If you recall, a circle has x minus h squared plus y minus k squared is equal to r squared. Well, what's the big difference? Well, first off, we know that this here, the right side, is equal to 1. So if I wanted that to look like the other, I would just divide everything here by by r squared, excuse me. And that's going to give me 1. Now compare the two. Well, now they look almost identical. The only difference now is that here we have a squared and b squared versus r squared and r squared. Well, if you think about it, it's because we don't have the same radius all the way around with an ellipse. With an ellipse, the value of A, here, let me just define this, the value of A is not going to be the same as the value of B. So for that reason, we can see that other than that, they're nearly identical. So in the context of what we defined previously with A and B, let's just make sure we understand that the standard form equation of an ellipse is x minus h squared over a squared plus y minus k squared over b squared. All of that is equal to 1. And one of the biggest distinctions that I can make here is about A and B. It's important for us to note and remember that A always represents the distance from the center to your vertex right over here. So if that is the case, A always lies on the major axis. A always lies on our major axis. And we're going to say that A is always the larger value. So what's going to be really nice for us is that when we're looking at the standard form equation of an ellipse, you just look at the larger denominator. Whichever one is your larger number, that is going to represent your A squared. If that's the case, then that tells you whether or not your major axis is horizontal or vertical. How so? When your A value is underneath your X, think of X as horizontal. When your A value is underneath your X, then your major axis is horizontal. Over here, compare that to this equation. This time our A squared is underneath our Y, in which case our major axis is now vertical. So it's going to tell you the orientation of the ellipse. And our definitions for A, B, and F, or A, B, and C, depending on whether or not you're going with a textbook variable, are all written out here. I'll let you pause the video and write these down if you need to. All right. Finally, the last thing that I want to discuss before we jump into some practice problems is the idea of eccentricity. And I'm just going to give you the most simple definition that I can with eccentricity. And it's simply how oval or ovally, I don't even know if that's a word, how oval your ellipse is. And we find our eccentricity by looking at the ratio between our F value, again, the distance from your center to your focus, to one of your foci, over A. Well, what does that look like here? Let's take a look at this particular ellipse. So again, the textbook uses C. I'm just going to rewrite that as F for both. Compare F to A in this case. Compare F to A if that is our eccentricity. F to A. Well, we see here that our E value is fairly small. I'm going to change that to F. It's fairly small, right? Looks like it's approximately 1/5 of the distance of A. Now compare that to this ellipse right over here. Now this time, compare this distance, your F value, to A. In this case, it's much higher, right? It's looking like it's closer to like 0.7 or something like that. So we see here that it has a greater eccentricity, therefore it's more like an oval. Our eccentricity is always going to be measured between 0 and 1. And just pause the video and think about for a second, what does that mean? if your eccentricity is 0? Well, if your eccentricity is 0, that means your ellipse is closer and closer, or I should say approaching 0, is closer and closer to that of a circle. If it gets closer to 1, then it's closer to that of a line segment. Imagine like a rubber band. If you were to pull on both opposite ends of a rubber band, you get something that looks closer to a line. All right, so with that all being said, let's go ahead and try some practice problems here. So in this problem, we're going to find the standard form equation of an ellipse, and we're going to find all this other information with it, like the center and vertices and yada yada. So let's go ahead and break this down. So first things first, take a look at this equation. You will notice that our A and our C coefficients, are not the same. They have the same sign, but they're not the same values. So that's going to tell us right away that this is an ellipse. And we'll talk in the next video about how you know it's going to be a hyperbola instead. But with that said, let's go ahead and start completing the square here. So I'm going to group together my x values. So I've got 9x squared plus 54x plus something to complete the square, plus 25y squared minus 50y plus some constant in order to complete that square. And I'm going to move this constant of negative 119 over to the other side. Again, there's a number of different ways to complete the square. This is the one that makes the most sense to me. Now, I always like to factor out my leading coefficients, so I'm going to do that. So I'm going to factor out that 9, so I've got x squared plus 6x plus some constant plus 25, and factor that out, y squared minus 2y plus something, and let's leave some placeholders for what we're about to add, okay? So in order for me to complete the square inside this trinomial here, I'm going to need to find half of 6 and square that, so that would make this 9. However, it's important to note that because we have a factored out coefficient here, we are then going to, in order for us to put 9 there, we're actually adding 81, or 9 times 9, to both sides. Same deal over here. Half of negative 2 is negative 1, but negative 1 squared is 1. So I'm going to then go ahead and put 25 there. So now let's clean this up. We've got 9 times x plus 3 squared plus 25 times y minus 1 squared. All of this is equal to 225. And because we want our right side to be equal to 1, we're going to divide everything here by 225. So it gives me x plus 3 squared over 25 plus y minus 1 squared over 9, and all of this equal to 1. So there's our standard form equation. Now, again, the primary purpose of this, and let me just make this a little smaller, the primary purpose of this is so that we can easily identify some of our key information. So pause the video right now and try to write down everything that you know just by looking at this standard form equation. Well, hopefully you said that you know that the center is at negative 3, positive 1. I know that a squared is my larger value, so that means this is going to be my a squared, which means that a is equal to 5. This 9 is my b squared then, which means b is equal to 3. And because my a is underneath my x variable, that means my major axis is going to be horizontal, a horizontal major axis. What else do we know? We know that there's a relationship between f, or the distance from the center to the foci, and a and b. It is written as such, and we got that again from the Pythagorean triangle or Pythagorean theorem. So we can say f squared is equal to 25 minus 9, which means f is then going to be equal to the square root of 16, or 4. So from here on out, I'm going to start jotting things down now that we know all this, but we're going to go ahead and graph this as we go along. So first off, if I know my center is at negative 3, positive 1, there's my center. Okay. I know that my major axis is horizontal, and my vertices are going to be located 5 units apart on each side of the center. So I can just count 5 this way and say, hey, here's my first vertex. Or I could just go ahead and add and subtract this to my x value of my center. So negative 3 plus 5, we said was 2. Negative 3 minus 5 is negative 8, 1, which means right over here. There's my other vertex. And I know that my foci are going to be 4 units away on each side. So let's go ahead and plot those. I'll do this in a different color. 4 units away on each side. So there's my first focus. There's my second focus. So I can write this as 1, 1 and negative 7, 1. My co-vertices are going to be 3 units on the top and bottom of my center. So I've got a co-vertex up here, and we have a co-vertex down here, 1, 2, 3. So there's my co-vertices. So I can write this as negative 3 plus, or 1 plus 3 is going to be 4, negative 3 minus, negative 3, 1, and that 1 minus 3 is negative 2. Okay, and now I'm ready to draw my ellipse. So again, like I said before, try not to just do this in one go. Do your best to kind of do this in quarter chunks. Remember that most ellipses look more like a rugby ball than they do a football. And this isn't fantastic, but for our intents and purposes, it works. Try not to do anything like this. Like this is just a bad. Like I've seen stuff like that. That's no good, right? That's a rhombus, right? Or even like trying to do like a block. That's not good either. All right, so avoid things like that. Just try your best. Take your time. You don't have to be an artist, but take about work at kind of a quarter arc at a time, if you will. All right. I think the only thing left for us to do in this problem is to find our eccentricity, which is just simply F over A. And so our F value is 4, our A value is 5, and we are all done. So go ahead and try this next problem on your own, and you can check your solutions with what I have in Google Classroom. The final type of problem that I want to do in this lesson is to talk about how to find the standard form equation of an ellipse, just given some information about it. And as I always recommend with these types of problems, it's nice to just sketch a graph. Don't worry about making it super detailed, but just to kind of visually see what's going on here. So if I know my vertices are at 3, 1, and 3, 9, so these are my vertices. Just this bit of information already tells me so much. It tells me that my major axis is going to be vertical. It also tells me that my center is halfway between my vertices. So it's got to be at the point 3, 5. At this point 3, 5. So if I know that the structure of my ellipse is the following, it's x minus h squared plus y minus k squared is equal to 1, and both of these over either a squared or b squared. Well, since I know that my major axis is vertical, that means this here is my a value. In this case, a is equal to 4. The distance from 5 to 9 is 4. That means my major axis is vertical, so my a squared has to be underneath my y term, and my b squared has to be underneath my x term. Since we know that a is equal to 4, we know that this is equal to 16. We also know that our center is 3, 5, so I can write x minus 3, y minus 5 there. And all that's missing now is my b squared, but that's where this bit of information comes in. And before I finish this, I just want you to kind of appreciate how much information we can get just from knowing where our vertices are. We're pretty much practically able to write the entire standard form equation, but we can't finish this without knowing our b value. Since we know that our minor axis length is 6, and we know that 2b, let me just do this in a different color, 2b is equal to 6, that means b is equal to 3. If b is equal to 6, that means, or excuse me, if b is equal to 3, that means b squared is equal to 9. All right, and with all that, we're then able to write our standard form equation of our ellipse from just those two pieces of information. So number 2 is a similar problem. I encourage you to try that on your own and go ahead and check my solutions that I've uploaded just to compare your answer.